Okay, so back at it. So if, like I said, this hypothesis testing, I'm breaking up into four sections. If everything I talked about for the first hour, or however long it was previously, was nugget number one, this will be nugget number two. And what it all really boils down to is, do you know the population standard deviation? In the first instance, we did. When we know the population standard deviation, we can use the z-statistic to test our null and research hypothesis. However, oftentimes it's the case that we don't know it. In the example of the HMO data, obviously some kind of national database has the national average and the national standard deviation. Similar to how like the census would have the U.S. Mean age and the standard deviation, or the U.S. mean income and the standard deviation. So, in some instances we do, but it's definitely more frequent that we don't know it. So when we don't know the population standard deviation, we need another test statistic. Z won't suffice. So if I could boil everything I'm talking about down into one little so what point, the question you got to ask yourself when you're doing these problems is, do you know the population standard deviation? If you do, then you're good to go with the z-score. If you know the population standard deviation, you can calculate the standard error and compute a z-statistic. However, if you don't know it, then we have to use something else to calculate the standard error, right? We don't know the population standard deviation. We can't calculate the standard error using it, so we need something else. The solution is to use a t-statistic. So when when we don't know the population standard deviation, we can estimate the standard error using the sample standard deviation, S, as opposed to the population standard deviation, sigma. And in that case, we use the t-statistic rather than the z to test the null hypothesis. Again, it's the same logic. You're just computing a test statistic to test your hypothesis. But if you know the population standard deviation, you can use z. If you don't, you got to use t. And that's what we're going to talk about here for the next, hopefully I can get through this in about 15 minutes. We shall see. Okay, so t-statistic, and if you look at your equation here, it's similar to z. So the t-statistic is equal to the sample mean minus the population mean divided by the sample standard deviation divided by the square root of n, square root of sample size. So the t-statistic is, don't think of it as anything different than the z-statistic. It's just what we use when we don't know the population standard deviation, right? Right here. It's the same thing. It's still the computed statistic we use to test the hypothesis, the null compared to the research. So the obtained t represents the number of standard deviation units or standard error units that our sample mean is from the hypothesized value of mu, the population mean, assuming the null hypothesis is true. It's the same thing. It's just like z, it's in standard deviation units. It's just slightly different. And what I'm going to show you is that t is a little bit more flexible. So the t distribution is different than the z. So the z distribution is the standard normal curve. It's the same always and forever. You've seen the shape. It is what it is. The t distribution, though, is a family of curves, and the actual shape of the curve is determined by what's known as the degrees of freedom. So it's used when the population standard deviation is unknown. So we know that. So it's a family of curves in the sense that it's not just the same, so z is always the same shape. But if you take a look, and this figure's in your book, the t-statistic can take different shapes depending on the degrees of freedom. If there are more degrees of freedom, then you approach a normal curve. The less degrees of freedom you have, I believe right, here it is. So when you decrease the degrees of freedom, so less degrees of freedom, the curve flattens. And hopefully we can do that with the COVID outbreak, flatten the curve, right? I mean, you guys have all heard about that. I've been looking at some of the data that they're using, and t-statistics is what they use because the actual shape of the curve is a little bit more, it's not fixed. So you can think of the z distribution as having this fixed shape. It's always a normal curve. Whereas the t, depending on the degrees of freedom, is flatter or steeper. So it's a little bit more flexible. Why is it more flexible? Well, because it accounts for us using the sample standard deviation as opposed to the population standard deviation. So it has to allow for a little bit more flexibility. And how is that done? Through the degrees of freedom. So hopefully you're thinking, okay, what's degrees of freedom? And I have a pretty good way of explaining this. It can be kind of fuzzy, but I have a nice little trick on this one. So the degrees of freedom are the number of scores that are free to vary in calculating a statistic. So it's basically, think of the number of observations in the data that are free to vary when estimating the statistical parameters. So let's say, the calculation's easy. It's just n minus 1. So if you have a sample of 50, your degrees of freedom would be 49. And if you had a sample of 100, your degrees of freedom would be 99. The way I like to think about it is, so if it's n minus 1, what does that mean when it means that the scores are free to vary? So think about 7. 7 is actually my favorite number for a variety of reasons. But think about 7 as in like the days of the week. So think about if you have 7 days in the week and you have 7 different hats you can wear. And again, it's a little bit of a corny example, but I think it works. So think about, so you have 7 hats that you can wear in a week. So on the first day, do you have a choice? Yes, you have 7 different hats. And I should specify, you can't wear the same hat twice. You got to be fashionable. Nobody wants to be repeating their wardrobe day after day. So you have 7 hats. You can only wear it once. You don't want to repeat. And you have to wear them all in a week. So on the first day, you have 7 hats to choose from. You have freedom, right? So you have the number is free to vary. On the second day, you still have 6 hats left that you could possibly wear, so you have variation there. The third day, you have 5 hats. Fourth day, 4 hats. Fifth day, 3 hats. Sixth day, you have 2 hats, so you still have a choice on the 6th day. But what happens on the 7th day? Well, you don't really have a choice. You only have 1 hat left to wear. So that's kind of how degrees of freedom work, in the sense that, so if you had a value of 7, you would have 6 degrees of freedom. Meaning that on 6 of those 7 days, you could wear a different hat. But on the 7th day, you've only got 1 hat left to wear. So you can think of degrees of freedom as sort of like when, having choices. So if you have 50 people, 50 people in your sample, your degrees of freedom would be 49. Because on that first case, you could have any of the 50. But the second, you only have 49 left, and so on and so forth, to the point where you get to the 50th, you only have 1 person left, so you don't have any degrees of freedom at that point. Like I said, the calculation is simple, but the logic behind it could be a little murky. But just think of the hats. Okay, so degrees of freedom is really simple to calculate. It's literally just the sample minus 1. Okay. So one thing to think about is, what are the similarities and differences between the Z and T statistics? So think back to the first kernel that I gave you in hypothesis testing, that if you had if you had the population standard deviation, you can use a Z. So this is the sample mean minus the population mean divided by the population standard deviation divided by the square root of the sample size. Now, if you look at T, what's really different about that? It's still the sample mean minus the population mean, so your denominator is the same. The numerator is the same, right? The denominator is slightly different, but it's only different in that you're using an S as opposed to a sigma. The sample standard deviation or the population standard deviation. So really, they kind of look the same. So you might be saying, why not just use a Z? Because they kind of, in the end, it kind of works out the same. Well, because we're using the sample standard deviation as an estimate of the population standard deviation, we have to allow for this. We have to allow for this flexibility, and that's where the degrees of freedom come into play. So with the T statistic, you're always going to have to calculate the degrees of freedom. Okay. So let's take a look at the book. So here's your standard normal table. This is the z-statistics, right? This is what you're used to seeing. So if you flip on over to Appendix C, look at the t-distribution. It's set up a lot differently. So there's a couple things you should notice here. One, we have the significance level for a one-tailed or a two-tailed test. So you can, this will be, depending on whether you're doing a one-tailed or two-tailed test for your research and null hypothesis, you'll look at these. And then look over here on the left side, you've got the degrees of freedom. Okay? So that's why you got to calculate the degrees of freedom first, and then get your t-statistic and compare it. I'm going to do an example here in a sec. I've already got that. This figure is really useful. Again, I'm just going to say it one more time. Please, please read the chapter. I hate that we have to be so reliant on the book, but such is the nature of the course at this point. Make sure you're reading. Okay, so back to our 5 steps. So hypothesis testing with one sample and population, with the sample and the population variance or standard deviation is unknown. So this is point number 2. We don't know the population standard deviation. In point number 1, we did. When we did, we used a z. When we didn't, we use a t. Okay, so it's the same steps as before. We make the assumptions, state the hypotheses, the research and the null, and select the alpha. We select the sampling distribution and specify the test statistic. Obviously, if we don't know the population standard deviation, we use the t. We compute it, including the degrees of freedom. Here's your equation, and then make a decision. Do we reject the null, or do we fail to reject the null? And how confident are we in doing so? Okay? And that's it for the slides. So let's do an example where we don't know the population standard deviation and thusly have to use a t-statistic. So let me pull this out here. Okay. Mark that so I don't have to keep flipping back and forth to find the table. So here's the question I want you to look at, and obviously these are, again, I'm using problems from the book so you can see. I don't like to do that normally, but again, it's the nature of the thing. I just think it's easier for y'all. So look at question number 5. So let's read it. One way to check on how representative a survey is of the population from which it is drawn is to compare various characteristics of the sample with the population characteristics. So it's basically, we get a sample, we can look at how representative it is, looking at sample means compared to the population means. Okay. So in this example, a typical variable used for this purpose is age. So we could, maybe look at age. So in the 2010 GSS, which, we've used before, the American adult population had a mean age of 49.28 and a standard deviation of 17.21 for a sample of 4,857 adults. Assume that we know from the census data that the true mean age of all American adults is 37.2. Use this information to answer the question. So we want to state the research and null hypothesis for a two-tailed test. You specify that. Calculate the t-statistic, and here we go. We want to look at the significance level at 0.001. So we want to be 99.9% confident here. Come up with a conclusion. And then what's your decision? And tell us about how representative the GSS is of the American population. Okay, so it's kind of like, so let's just go through what we know. So we know the population mean. We know the sample mean. Right, here's your sample mean, 49.2. We know the population mean. And we know the sample standard deviation. But we don't know the population standard deviation. So if we don't know the population standard deviation, we can't use z, we got to use t. Okay, so the first thing we want to do is write out our null and research hypotheses, always and forever. Always stated in terms of the population parameters. So the null hypothesis is going to be that the mean age is equal to 37.2. Okay? The research hypothesis is going to be that the mean age is not equal to 37.2. Hold on one second. Get organized here. Wait a second. Sorry, give me 1 second. I just want to double check that before I move on. Okay, cool. Okay. So basically what we're saying is that the sample that we get where we had, so what was our sample mean? It was sorry, holding this phone up takes 1 degree of freedom away from my hands. 49.28. So this was the sample mean we got. This was the population mean. So what we want to know is the population mean that we got, is it actually 37.2? Or in this case, is it not 37.2? So I'm doing a two-tailed test here, not equal to. You might ask why? Or you go back to the question here. Specifies right here, two-tailed test, okay? So these things are always gonna be kind of spelled out for you. It's not like I'm guessing at that. Now, if you were doing this on your own, you would want to do a two-tailed test if you didn't have any theoretical reason to believe that there would be a higher or lower difference, but let theory kind of, when you're doing this stuff on your own, for those of you who are gonna be doing more work on your project, let the theory kind of guide what type of test you do, okay? But in these examples, just let the book tell you. Okay, so here's our null in research. Our alpha is equal to 0.001, and you might ask, where did that come from? Again, straight from the question. That's the threshold that we're going to use. Okay, so to calculate the t statistic, we have x bar minus mu divided by the sample standard deviation divided by the square root of n, which gives us 49.28 minus 37.2, right? Sample mean, population mean, divided by the sample standard deviation was what, 17.21, divided by the square root of 4857, which is our sample size. Okay, I've already calculated that out. It's 12.08 divided by 0.25. 12.08. 17.21 divided by root 4857 is 0.25. Okay, so we're going to get a t statistic equal to 48.32? Yeah, 48.32. Okay, so that's our t. Okay, so if you look back to the steps, we've made, and again, I'm being kind of sloppy with this. If the sample's not randomly distributed, or you're not using an interval ratio level variable, or the sample size is less than 50, we cannot assume, we cannot make the assumptions that allow us to go forward with a hypothesis test, and that would be the end of it. So if any of those assumptions don't hold true, we can't do a hypothesis test, okay? We saved the research and null hypothesis, selected alpha. We selected the sample distribution because we don't know the population standard deviation. We have to use t. We computed the test statistic right here. We got our t. But we also have to compute degrees of freedom. And this might be the simplest calculation you've ever done. Obviously, degrees of freedom is equal to 4857 minus 1, right? N minus 1. So 4856. So you have 4,856 degrees of freedom. Okay, so now you've got your t, you got your degrees of freedom. Let's scooch on back to Appendix C of the book. And let's get used to reading the t-table. The first thing you want to look at is what is your level of significance? Are you using a one-tailed or a two-tailed? Well, we're using a two-tailed, and we're using a significance level of 0.001. The most stringent we have, that's the 99.9% confidence level. So we have our degrees of freedom, 4856. You look over here on the side, down to 25, and you go up here. So if you see this is infinity. So anything above 120, we're going to use these as sort of our cutoff values. Okay. So if you're looking, so where we should be looking here is we have degrees of freedom over 120. So it's going to be here. And then we're looking at a two-tailed test with alpha, the cutoff of being 0.001. So this is the number we're going to be looking at right here, 3.291. Right? Okay. So what you will, do I have that in the slides here? I may need to add this. Yeah, I'll have to add that. But basically what you do is if your calculated t statistic is greater than the threshold value determined by your alpha and your degrees of freedom, if this number is greater, then we reject the null. Okay? So that's kind of a difference there. So in the Z, we were taking the Z-score and getting a p-value and seeing if the p was less than alpha. So the probability being less than alpha. In this case, we are comparing our test statistic, which is 48.32, so 48, compared to a t threshold. In this case, if the t value that we calculate, if the test statistic is higher than this value, then we can assume that the differences were not. I guess the difference between the sample mean and the population mean they are not. The difference is not by chance alone. So in essence, if it's greater than this number, then you can be sure you can assume that you have reason to reject the null hypothesis. Let's say you got a t value of say say you got a t value of 2.3. Well, if under the same criteria with the same sample size and the same alpha cutoff level, if you got a t of 2.2, 2.8, whatever I said, 2, if it's less than this number, then you would fail to reject the null. So that's one kind of minor difference there, and it's, if you think back to when we calculated the Z, we got a Z that was really high. So basically, if you get here we got a T score that's really high. Before, when we got a Z score that was really high, then we look at the probability. Well, here we're not looking at the probability; we're just looking at the T score itself. So if it's higher, then we reject. If it's lower, then we fail to reject. So in this case, obviously 48 is much higher than 3.2. So we would reject the null hypothesis in favor of the research hypothesis. So just to put it in like kind of a Mad Lib form answer, how you would answer that would be, always start out with how confident you are. We are 99.9% confident that the sample mean that we calculated is different from the true population mean. So going back to this question, looking at is the GSS representative? In terms of age, it's not, because the GSS, the average age was 49.28, but in reality it's 37.2. So we can assume that these two numbers are statistically different from each other. And that's kind of it. So like I said, there's 4 kernels here. We've done 2 today. So the first was we're comparing a sample mean to a population mean When we know the population standard deviation, then we use the z. That was procedure 1. When we're comparing a sample mean to a population mean and we don't know the population standard deviation, that's procedure 2. We use the t-score. So let's let that sink in a little bit. Please do maybe a practice problem or two from the book. Read the chapter. It's just, we've kind of gone through. We've done about the first 2/3 of chapter 9. The next two things that I'm going to show you aren't any different in terms of the logic or procedure. It's just slightly different in that we're going to be comparing two sample means. Maybe hold on that. Don't worry about that for now. Just know for now that what did we do in part 1? We compared a sample mean to a population mean to see if they were different. We used a z test statistic because we knew the population standard deviation. In the second case, we're still doing the same thing. We're comparing a sample mean to a mean to a population mean. But in that case, we don't know the we don't know the population standard deviation. So we don't know the population standard deviation, but we do know the sample standard deviation. Then we got to use t. But it's the same logic. You're still comparing a sample mean to a population mean and seeing, is it significantly different? In which case we would reject the null and favor the research. Or is it not significantly different? In which case we would fail to reject the null or accept the null. And we would not be able to prove our research. Going back to the innocent and guilty analogy, we have to assume innocence until we can prove guilt, I guess, in essence. Okay, so that is all I have for you today. I'm gonna let that sink in a little bit, and then I'm gonna add a couple more layers tomorrow, and then I'm gonna post your assignment. I'm going to keep the assignments as straightforward as possible. I'm going to do them, I'm going to make them as similar to the examples as I can. The other thing I want to say is that, I know that this is, this is not ideal, obviously, but as long as you are putting an effort and trying and I can see you're spending time with this, don't worry about your grades. Part of my thinking is that you all paid for a course that has been severely interrupted, and I can't get you a price reduction on the course, but I can make sure that you receive ample credit for it. So take of that what you will, and hopefully you can get what I'm alluding to, but please just stay up to date with everything. Ask me questions if you need them. Turn everything in. As long as you're putting in effort, I'm going to take care of you grade-wise because of everything that's happened. I just don't think, from a financial standpoint, it's fair to penalize you, for this. So do your best. I know this is not ideal. Trust me, this is tough for me. So. Let this sink in a little bit, review these slides, ask questions, and then tomorrow I'll hit you with some new stuff. But keep up the good work and stay on top of your social distancing. So talk to you tomorrow. Bye.